So just like we had rules for exponential functions, we're going to look at rules for logarithmic functions, all right? So let's look at the first very basic thing. So first of all, again, we know that the base, right? So a is greater than 0 and a is not equal to 1, right? So our base for the log is always going to be greater than 0, just like for exponential functions, and it cannot be equal to 1, all right? So the first rule, what is a log of 0 to the base a? Well, let's see. So if I wrote this, suppose it was x, I don't know what it is, right? So let's suppose that log of 0 to the base a equals x, right? What is this exponential notation? Exponential notation is going to be a to the x equals 0. Now let's think about it. When does a to the x become 0? Well, never, right? Because if you remember, your exponential function never touches the x-axis, so that value will never become, right? This value can never become 0. In fact, our range was from above the x-axis, open interval 0 to infinity, right? So this is not possible. So this does not exist. I mean, I cannot calculate the log of 0. Okay, no matter what my base is, I just cannot calculate the log of 0. Okay, same thing. What is a log of a negative number? Okay, again, this graph for my exponential function will never go down, right? Or think about now the graph of your log function. We know what the graph of a log function looks like. Okay, and the domain of my log function, right, it doesn't include 0, so obviously that doesn't happen. But the domain also doesn't go past the y-axis, so I cannot take logs of negative number because negative numbers are not in the domain of my log function, right? The domain of my log function was all positive numbers are from 0 to infinity. So this is also does not exist. Okay, then third one. What is the log of 1 to the base a? Well, so we can look at it a couple ways. One we can do is, let's write down the corresponding expression. So suppose that it was y, right? So suppose that log of 1 to the base a was equal to y. What's my corresponding exponential expression? Well, then that one is going to be a to the y equals 1. When does that happen, right? That only happens when y equal to 0. Okay, so this would have to be 0, right? So that's property number 1, property number 2, or rule number 2, and rule number 3. Now, rule number 3 is also evident from the graph, right? Because what happens when I put x equal to 1, right? If fx was equal to log x, this is nothing but f of 1. When I put x equal to 1, it touches the x-axis, rather it crosses the x-axis at that point, and so you can see that this is my point 1, 0. So at 1, the y value has to be equal to 0. All right, so let's look at property number 4. So we have log of x times y to the base a equals log of x to the base a plus log of y to the base a. All right. So remember, when you're multiplying something inside a log, that ends up being the sum of two logs. Okay. As an example, we can say log of 3x to the base a is log of 3 to the base a plus log of x to the base a. Okay. Now, just like I told you in exponential functions, there's a room for error here, and one of the most common mistakes is people write log of x plus y to the base a is equal to log of x to the base a plus log of y to the base a. That is incorrect. Okay, this only works if you're multiplying things in the log and not when you're adding. There is no rule for this addition here. Okay, all right, let's look at property number 5. So log of x over y to the base a. Okay, this can be written as log of x to the base a minus log of y to the base a. All right, so as an example, you could say log of let's see, 5 over 7 to the base 2 is nothing but log of 5 to the base 2 minus log of 7 to the base 2. Okay. Now again, a common mistake here is log of x minus y to the base a is log x to the base a minus log y to the base a. All right. Just like for addition here, this is incorrect, and there is no formula for log x minus y to the base a. Okay, it's log x over y is log x minus log y. Let's look at one of the most obvious properties, which I should have done earlier. So what is log of a to the base a? Well, let's think about it. So let's say that was equal to y. So let's say log of a to the base a was equal to y. Our exponential function indicates here that a to the y should be equal to a. When does that happen? Well, when y is equal to 1, right? So this is equal to 1. So if you are taking the log of a number and that number is the same as the base of the log, then that will always equal 1. So for example, log of 5 to the base 5 is going to be equal to 1. Okay? Then number 7, log of x to the n base a. All right. So in this case, what we can do is we can take this n and we can replace it as a coefficient here. So this will be equal to n times log x to the a. Right? As an example, log of 5 cubed to the base 2 is nothing but 3 times log of 5 to the base 2. All right, the last two rules are the ones that we call the inverse function property, right? So this is the inverse function property. If you remember, right, if I composed inverse functions, if I did f(of) inverse of x, that was equal to x. If I did the other way around, f inverse of x, well, that was also equal to x. Well, since logs and exponents are inverse functions, we have similar properties for them as well. The first one of those, so let's call that number 8, and that one is going to be log of a to the x base a is equal to x. All right, and then number 9, a raised to the power log of a to the x is also equal to x. All right, so as an example for this one, we could say log of 2 to the 5 to the base 2 is equal to 5. And here I could say 3 to the log 10 base 3 is equal to 10, right? So these will come in very handy when we start solving equations with logs or equations with exponents, all right? So just know that if the base of the exponent and the log are the same, we get our variable back.